I'm John Wilker, the organizer of 360 IDEP. I hope you enjoy this session recording, but first I wanted to mention one thing. We've served the community since 2009, and over the past few years we've had to take on debt in an effort to keep the conference alive. After several unforeseen challenges, not the least of which is a pandemic of indefinite duration, we've had to make the hard choice to end the conference as we're now facing over $100,000 in debt. As a result of requests from the community of how they can help, we've created a GoFundMe campaign. If you're inclined and able, please consider donating to help keep 360 IDEP going. The QR code after this will link you to the campaign. Thank you. Enjoy the recording.
Great. I'd like to thank you all for coming to my talk and not to Josh's. That means a lot to me. Yeah. This is how not to create an detector using CreateML. I'm Yono. And we're going to start, despite advice given to me by smarter people, with a live demo. This live demo is going to listen to my live audio. It's going to run a core ML model in the background. It's going to analyze it for anytime I say and it's going to make predictions every half a second and count my shame. It's not working because when I tested this in my room in front of my computer, not in a giant room echoing with my microphone. So if it doesn't work, it's a lesson that we can learn from. It's intended, okay? Also, I'm running on my laptop, I'm running Keynote and this core ML model in the background. I'm pretty sure everything should work. Nothing should explode, but just to be on the safe side, we're gonna put on some safety goggles. I believe John has put them underneath your seats too, I hope, all right? Oh, never mind. Okay, well, so who am I? Along with Alice Zhao, I'm the co-creator of Gus on the Go, that cute little guy right there. I am a freelance software developer specializing in computer vision and iOS. I know what you're thinking right now. An detector doesn't sound like anything to do with computer vision. It's too late, you're stuck in this room now. I am a tutorial writer for RayWenderlich.com, and one time a neighbor called the cops on me for running a meth lab out of my apartment. The joke was on her, I was brewing beer. All right, story time, it's not about the meth lab. Last year, I was at this very conference, between talks, sitting in the very back of the room. Next to me, I was sitting next to Joe. I turned to Joe, and I said, "Hey Joe, what are you working on?" "Oh, hey Yana, I'm just editing some release note audio before the next talk starts." Huh. That's cool. Does your software let you automate a lot of that editing? Some of the stuff, yeah, but it would be nice if it could edit out these ums. They're kind of tedious. Huh. I think I have an idea on how to do that. We could probably use machine learning, train a model to detect ums, and maybe even cut them out automatically if it's reasonably sure that they're there. But I would need a lot of data for that. I've got a lot of data for you. Really? Then I was happy. I had such long, beautiful hair back then. So we can do this maybe, but why would we want to? Besides, of course, content for a talk at a conference. Okay, so why do we want to do this? Well, who needs this? How many of the people in the room here have a podcast? Raise your hands. Okay. I saw 3 hands go up. How many people lied about not having a podcast? I'm sure it's more of you, right? So we've already determined podcasters are a target audience for this kind of product. And in general, we can generalize that to just audio editors in general. If you have public speaking training, that would be kind of good because the less time you say the more professional you sound. Anybody else have an idea of who might need this kind of product? Yeah? Yeah, I mean, public speaking trainers, right? Look, I'm looking for product market fit here. If anyone has any ideas, come see me, okay? And maybe YouTubers could use this, I don't know. All right. This talk is also not really about code. There is some code in it, but that's just to appease those of you that expect it. It's more about a thought process. It's mostly by example. I'm going to show the thought process I go through in creating a machine learning model, how I decide what kind of data I need to collect, how to collect it, and how to compare iterations of my various models. The idea is just because you try it once doesn't mean that you're done. It's an iterative process. So how do we detect ums, which is clearly not working right now. So what is an anyway? It's kind of this like monosyllabical something, right? It's kind of like a word, but it doesn't have any meaning. It's a filler, kind of like, which I keep saying also. And if it's like a word, maybe we can use speech recognition to detect our ums. This was my first attempt. Speech recognition is available through Apple's speech framework. And it's easy to use, and it's built in. I said those backwards. So I'm going to show some code now. This is the token code I was talking about, for those that expect it. We're just going to instantiate our audio engine to grab our microphone input. We then need to get the output format of the input node, which is kind of a weird naming convention. But if you think about it, an input node is an object, takes microphone input, and has an output. So you have output from your input. I mean, naming is hard, right? Okay, so we have our format of the data, and we need to install an audio tap. We need to install an audio tap on our input node. We then take the buffer that we get from the audio tap, add it to the request. What request you're asking? Well, the SF speech audio buffer recognition result or request. Also, again, naming is hard. And then we run this and test it out, and we find out it doesn't work. Apple's speech recognition behind the hood is filtering out stuff like uhs and ums, because when you want to do dictation, you want it to transcribe something, you don't want it to actually transcribe those things. So they're automatically filtering it out. However, we didn't even have to write this code. We could have just tried out stereo dictation on our watches or our phones. And in this case, we can create an ARM detector, or my favorite, we can create an M detector, which I guess is useful for James Bond. All right, there is a hack to get it to work. If you create a contact and you name it it will try to detect ums, because it detects people's names in your contacts, sort of. It doesn't detect it as a filler word, but just in a place of a sentence where you could have replaced it with somebody's name. So I was talking to Joe, then it would detect the But if I was just saying in front of something else, it wouldn't work. I also could not get it to work for just All right, back to our original question then. How do we detect ums? All right, attempt number 2, machine learning. So machine learning is the science of getting computers to learn without being explicitly programmed. And as software developers, this is what we should actually strive for if you think about it. Why do we get into software development? To automate stuff. We were lazy, we want things to work automatically, we don't want to have to do things manually. Imagine we could just tell a program what we want it to do, and it would figure it out on its own. That's the dream. That would give us more time for beach vacations, or playing video games, or if we're being completely honest with ourselves, more coding. All right, back to machine learning. What do we need for machine learning? Haha, first step, lots of math. Everyone here likes math, right? Oh, that's good. We need a data set, lots of data. We need a way to train a model. And we need a way to test a model. The nice thing is, these last two things can be covered by CreateML if we don't know how to do them ourselves. It's an easy way to get into machine learning. The other nice thing is CreateML does away with this first requirement of knowing lots of math. So you can get into it without even having to know about gradients and chain rules and stuff like that. All right, let's talk about the data set, which is arguably the most important part of the entire process. This is where the saying garbage in, garbage out is really applicable. If your data is terrible, your model's gonna be terrible. We take raw audio files, and we have two files here, one from Joe and one from Charles, from episode 432 of Release Notes. It's a good episode. Go listen to it. You'll notice Joe is a little bit smaller than Charles. It wasn't because Charles just kept talking after Joe hung up. Charles recorded in 2-channel 32-bit, Joe 1-channel 24-bit. That's the discrepancy. Took me a little while to figure out why. We're going to cut them into 1-second segments. Why 1 second? Because CreateML's sound analysis model defaults to 0.97 seconds for its buffer. And if you try to cut audio to 0.975 seconds and you get it off by just a little bit, then it's going to ignore it completely. So you go a little bit longer to make sure it handles all your data. How do we cut it into 1 second segments? That sounds like a lot of work through Audacity or something like that. Well, we can use FFmpeg. If we pass in our input file, we tell it we want to segment. We tell it the segment time of 1 second. And then we copy. We don't want to filter or anything like that. And we give it an output file name. In this case, it's going to go into the path Joe, and then it's going to number them 432 underscore, and give it a 5-digit number, 0 padded. And suddenly we have this list of files right there to go through. We now need to sort them into category. This means we have to listen to each file and determine whether it's clean or an This is the waveform for a clean audio. And if audio is working, oh, all the little circles. That was Charles saying something that had no ums in it whatsoever. And this is an example of also Charles. Now we all know what an sounds like when we're going through them. But you might have noticed in this picture, there are more categories than just clean or When I started working, I quickly ran into the situation where we need more categories because there's a lot of silence. When two podcasters are talking to each other, they're not usually talking over one another. One person is silent while the other person's talking, and back and forth. Well, silence doesn't teach our model much. This is like taking zeros and multiplying it through your model. It's not going to learn anything from it. There are no features to learn from it. This is, by the way, what silence sounds like. You catch that? All right. Additionally, there's also uhs. Uhs are a little bit different than ums. I wasn't sure initially if they were going to be treated the same or if they're completely different categories, so I decided to separate them out anyway. Oh, this is Joe now saying
You don't need all of them.
So he said it there at the beginning. Can anyone tell the difference between this waveform visually and the clean one? I can't. I have to actually listen to all of the files. And then we have this situation of unknown. And this comes up for a couple of reasons. Imagine we just get a cut of the audio where it starts now with an It could have been cutting a word in the middle where it's like fulcrum or spectrum or sum, or if you're British, mum. And if the clip ends in an it could be the beginning of a word like understand, umbrella, or unknown. And in this case, this is also Joe.
You're going with two.
At the very end there, he kind of did a laugh that sounded like an And I wasn't convinced that I would be able to tell the difference. And if I can't tell the difference, a model's not going to be able to tell the difference probably. So these unknowns get sorted into a separate category. Now this might seem tedious. If a podcaster talks for an hour, that's 3,600 files. If there are two hosts, that's 7,200 files you have to go through. Well, I did a lot of this on the plane back home. I do live in Germany, so it's a long flight. But I was able to use the touch bar to make things a little bit easier. Everyone loves a touch bar, right? So if you see here, as I'm going through Finder, Preview, clicking it, it actually shows me the waveform of the audio that I'm going through. It allowed me to quickly filter out any silence, which is over roughly half to over half of the audio file. So that got rid of a lot of them right away. I miss you, touch bar. All right, so we've sorted them into categories. And now we need to leave some for testing, which is very important. It's not hard because I didn't go through all the audio. It's a lot of work, like I said. But now we're ready to start CreateML. We've got our data set. We're going to open it up and create a sound classification problem. So we're going to classify sounds. Apple has some built-in ones that classify sounds like lion's roars or baby crying or airplane sounds. We're going to try it with ums. We're going to set the project info. We're going to add our data set to where this big plus is under training data. And if you notice, there's a, oh, sorry. It expects your data to be in a certain format. You need to have a folder for each class, and then you need to have these sample files underneath those folders. So in this case, we got rid of the unknown and the silence folders because we don't want to use those to train our model, as I said earlier. All right, we also have 2 versus 3 classes. We have, initially we wanted clean and and we quickly find out there were uhhs, the 3rd class. However, 3 classes was not actually good. I found that the model had trouble deciding between an and an very quickly, because basically has in it. Additionally, when they're split up like this, you're splitting up your uhhs and your into 2 separate categories. You have less data of each of them, less examples for the model to learn from. So what I did was I actually combined uhhs and ums into a single category called but we're still going to call it an detector because that sounds better. All right, so we add the data set, and now you see it tells us we have 2 classes, 736 examples. Over on the right, it says validation data. And it says it's split automatically from the training data. Validation data is data that your model is going to test itself on after each iteration, but it can't be seen by the model during training. The idea is it wants to train on certain data and then test to make sure it's actually learning something. If it's not learning something, it can actually stop early. All right, then we're gonna click this button to train, and we watch it create we extract features. So it's gonna extract features from all your audio files first. These features are nothing more than vectors of numbers, and it's gonna train a classifier on top of that. And this is what our first example is. So we have 100% training accuracy and a 91.1% validation accuracy. The 100% training accuracy, it's probably starting to memorize data. There shouldn't be 100%. The 91.1% validation accuracy, it's okay that it's lower than training because this is unseen data. It's never seen it before. We're going to test it subjectively first. So I had a clip from the audio from Joe and Charles that I would listen to, and you can do in the live preview, or not live preview, you can drag an audio into the preview file and then hit play, and you'll see that at the bottom it starts detecting as we go along. At the very beginning, it detected an which is incorrect. But it did get one that was correct later on, and it missed another one at the very end. So subjectively, it was okay, not great, but it was okay. Objectively, we can also add a test data set. So I took more data that wasn't classified before, and I added it to the test set. And that gives us 2 classes, 246 items. And it gives us this matrix here, which is called a confusion matrix because it's confusing. But it gives us precision and recall, even though it gave us accuracy for everything else. Since this is just 2 classes, we can convert recall into accuracy by using this math. I'm sorry, I said not math, but this is just a little bit of math. I did this for you anyway. And that comes out to 89%, which is about the same as our validation accuracy. So it's okay, not bad. All right, it works. We're done, right? Sort of. We have a few problems with this, though. All right, 3 problems. First one is voice diversity. Let's talk about that. This works pretty well for audio recorded by Charles or Joe. And there's Charles and Joe. It works pretty well for me, even though my demo is not showing that. But it did not work for my wife, and it did not work for my children. The reason it works well for Charles, Joe, and myself is I trained it on Charles and Joe's voices. And you might notice we are all adult white males with somewhat deep voices, Joe especially. And this is a problem. If you're only listening to podcasts with white adult male hosts, you might want to expand your horizons, but we're not gonna be able to teach a model how to detect higher pitch voices or even lower pitch voices using just these examples. All right, the next problem is we have an unbalanced data set. We had 1 or for every 11 clean data. That means we have significantly less data for the model to learn how to detect uhs or ums. This is a problem we'll get back to later. And we have labeling data is manual and time intensive. But in order to fix those first 2 problems, we need to actually tackle the 3rd problem head on, and we need to go to our next iteration and collect more data. But how do we collect more data? I didn't use all of the data from the initial recording, so what we're going to do is we're going to use our model that we just trained to pre-label data for us. So we run it on the rest of the data we had, and we let it label it for us. We do have to still check that data, but it's much faster than just listening to it and deciding for yourself. So to use a model in a Swift script, you need three things. You need an SN request, you need SN results observing, and you need an SN audio file analyzer. First, we'll create the request. I'm going to go through this quickly because, again, it's not about code. We are going to take the default configuration for the ML model. We're going to instantiate our sound classifier, which is called the Detector. We're going to create a sound request from that core ML model. And now we'll create the results observer, which is just a class that conforms to NS object and SN results observing. We only need one method for that, officially, and it sends us the results every time it analyzes a second of data. We take the SN classification out of these results, and we get the identifier of the class it detected, so clean or and then the confidence level of how sure it was that, that it was in clean or And then we instantiate the results observer. Finally, we need the analyzer, which just is an SN audio file analyzer with the audio URL. We add the request and the observer to it, and we analyze. Okay, so if we run this script now on the rest of the data, we get more. We started off in the initial time. We had 681 cleans, and we bumped that up by about threefold. We had 51 ums. We bumped that up by threefold. I didn't do all of the data. I got tired after a little while, so I stopped at this. But we're going to just train another model with this. So we add the data set with more data. We retrain, go through the entire process. Our training accuracy went down a little bit, which means it's not memorizing all our training data, which is good. Our validation accuracy went up a little bit, which is also good. Remember this number of 94.3. The last time it was 91.1. If we go back to this slide here, you might notice if you take the number of clean and divide it by the total, it's 92.5%. This is a little bit of a problem because this means that first time we got a validation accuracy of 91.1%, which is lower than this. That means we could replace our model with a script that just outputs clean all the time, and it would be more accurate. This second iteration, however, we have 94% higher than this, so it's actually having to learn something. All right, our subjective test, we fixed that first error where it was an and now it detects it correctly as clean. It still misses another later on and detects another one. So it's getting better, definitely, subjectively. Our objective test, if we take our confusion matrix and convert it to accuracy, we get 90%. So it improved slightly, which is good. But what does this do for us? We just trained on more data of Charles and Joe. So it improves the accuracy of the data of the model for Charles and Joe. It does nothing for women or children. So we're going to do something about this with even more machine learning. We're going to augment the data. This was my first attempt at trying to make it a little bit more robust for other people. And that means we're going to synthetically change our data to make the model more robust. In this case, we're going to randomly change the pitch of some samples, and we're going to randomly add noise to some samples. We'd ideally do this on the fly, but CreateML doesn't let you do this through the app, so we're going to pre-bake it, and it's fine. So how do you do this? Well, you could use Apple's audio frameworks, or you could use a command line tool called SOX, which is already built and less code to write. So SOX is sound exchange. It manipulates waveforms. You can change the pitch, you can change the loudness, you can add white noise. And you can install it via Homebrew, so it's easy. So really quickly, how do we do this? SOX is the command. We're going to pass it the example file. We're going to save it to a temporary file, and we're going to change the pitch by 400%. We're going to decrease the loudness by 10 decibels. We're then going to run the command again on our temporary file that we just created that has the pitch changed and the loudness changed. We're going to synthesize white noise at a certain volume. And this white noise synthesis doesn't actually put it on top of the file already. It just creates a waveform, or it creates a file, audio file that is the same length of just white noise. So we didn't have to pipe it back into SOX, merge it with our temporary file, and then save it to our example augmented file. So what does this sound like? Right? Oh, no, sorry. Let's say you want to use socks in a script with Swift. I didn't do that. I used Python, but I found this on Stack Overflow for you. It works. I tested it out. You can just use it. It'll be up in the slides later. That's how you use it. All right. So here is an example of Charles' voice made higher. It's a little bit like Alvin and the Chipmunks. And here is an example of Joe's voice made lower and louder, and it clips a little bit.
If you bring it.
Oh, geez. Yeah, sorry. That was louder than in rehearsal. All right. So we've augmented data. I want you to look at one thing. I did not augment any of the clean data. I only augmented our data because we had such an unbalanced data set. We don't need more clean data. We need more ums. So we increased our ums by 4 times. Now instead of a 1 to 11 ratio, we have a 4 to 11 ratio. All right, we add the new augmented data set. We retrain. And we see our training accuracy is 100% again, which is a little bit weird. Our validation accuracy is 95.7, so it's gone up quite a bit. Objectively, I didn't do subjective tests anymore. Objectively, we calculate a 96% accuracy from this, which is fantastic. There is one slight change here, is we changed from using Apple's audio feature print to using VGGish. You can have 2 different types of models to extract the features from the audio. Apple's audio feature print is 5 kilobytes when you save it to disk, and the VGG is 4.6 megabytes. The reason Apple's feature print extractor is 5 kilobytes is because their base model is already baked into iOS. So everyone's phone already has it. So all they do is ship the classifier that's added on top of it, whereas VGG, you have to have the whole model. The reason I switched here is because I found that after having a certain amount of data, it was working significantly better than Audio's framework, or Apple's audio feature prints. All right, so what does this do for us? It improves the accuracy and robustness of Charles and Joe recorded audio, like before, and it improves the accuracy for women and children. It started to work for my wife a little bit, which is great. It's not perfect because I don't think any of you confused Charles with a woman in that example earlier. But it does help a little bit. All right, so now what can we do? Well, we're gonna have to bite the bullet and get more data. Or should I say lower data? Sorry, that was a really bad joke. All right, more data. Where do we get more data? Well, you could record your own audio, but then you still have that voice diversity problem, because if you record your own audio and you mix it with, say, Charles and Joe's audio, you still have then 3 people's audio. And that's not going to help for a lot of people. You could find more podcasters, I guess. Or maybe there are open source data sets. I did a little bit of searching around, and I found Libre Speech, which is 1,000 hours of English speech, but it's based on public domain audiobooks. When people are reading books, they generally are not inserting uhs or ums into it, so that's pointless. I found Harper Valley Bank, which is simulated contact call centers, which is great. People were saying uhs and ums, but it's a call center audio, so it's all 8 kilohertz, which is not very useful. And then I found People's Speech. People's Speech I heard about on a podcast. You might see a theme in this whole talk about podcasts. It's licensed for academic and commercial use, so you can use it to build a machine learning model if you want and actually sell it. So we're good there, once we find that market product fit. It's 30,000 hours of transcribed audio, and it's diverse speakers, which is great. The transcribed part, it doesn't actually transcribe the uhs or the ums. I tried. It would have made it easier, but it doesn't. It's 2 terabytes of data, which is a lot of data. It's too much data. All right. This is where active learning comes in. So how are we going to go through all that data? Well, we can run our current best model on a subset of the data. We have it determine where the uhs or the ums are in the clean data, and we have it filtered out into buckets of confidence. So it's 50% confident, or in the bucket between 50 and 60% confidence of clean, or uhs or ums, and we use that data to train a new model. And then we can optionally rinse and repeat. So after every time we create a new model, we could have it tackle another section of the data, go through, label the data, and then train another model. The buckets that I was talking about, so we're going to use a Swift. Try this again. I'm sorry, it's like midnight for me, so I'm a little bit tired. I'm going to go through this. I'm going to get it. All right. We have this Swift. We're going to create a Swift command line interface to run inference on the audio. Inference is when you run your machine learning model and you give it some input and you see what the output is. We're going to sort the files into buckets of confidence levels. So as you can see here on the right-hand side, we have clean 50, clean 60, clean 70, clean 80. Those are the buckets of the confidence levels of how confident was it was clean or how confident was that it was ums. We're going to start with the least confidence file. So we're going to start with 50s and then sort those properly. We're going to do clean 50s and we're going to sort those properly. 60s, sort those properly, and so forth. And the reason we want to start with the least confident ones is because those are the examples that the model's having trouble with. So if we can sort them properly and then retrain a model, the idea is it'll get better at the harder examples. We're giving it hard examples to work on instead of easy ones. And I actually generated 2.5 hours of data from that 30,000 hours, but I only ended up using 13 minutes because, one, it's still a little bit time consuming. I got tired. And also, I went through the 50s, 60s, and 70s percentile, or the confidence levels for clean and and just used those. The vast majority of them were in the hundreds or the 90s, and those wouldn't have helped the model learn much new stuff. So after we add the active learning, we have more data. We could have done it even further, but I ran out of time. We add the new active learning data set to the create ML. We retrain. We get 100% training accuracy. Our validation accuracy went down a little bit. That's okay. We look at our objective testing. This is also a little bit different. We're testing only on Charles and Joe. So this model theoretically should be better at more people, but we're just testing on Charles and Joe. So the testing, we're comparing it, testing apples to apples with our previous models, but not necessarily with what it can actually do for everybody. And we get 94%, which is a little bit worse than that 96%, but it's probably because it's now generalizing to more people as opposed to specializing on Charles and Joe. Right? Wait a minute. The name of the talk is how not to create an detector. So why shouldn't this work? Are we really using the right tool for the job? I mentioned earlier that sound classification is used for stuff like detecting lion roars or baby crying or airplane sounds. Ideally, we'd have speech recognition without the filtering, the automatic filtering that's in there. Speech recognition and sound classification are two different model structures. And this method also introduces difficulties that are a little bit harder to overcome. If my live demo had worked, it would have been very apparent. What difficulties am I talking about? Sometimes people say the as the. Pass me the watermelon. And that sound would get detected as an A pronounces as I want a banana. That also sounds like an And then I've also mentioned already words that begin with like understand or umbrella. And different accents would also be troublesome. We talked about voice diversity, but not accent diversity. So this model that we've trained is going to work fairly well on American accents, but it's not going to work, say, on a British accent or an Indian accent or somebody else's accent. But it worked well enough. You have to trust me on this, because the live demo didn't work. It worked well enough. The live demo is also an example of I created this model, and it worked in my little setting for me in front of my laptop in a quiet environment, not in a large room echoing with my microphone. In order to get the model to work in this situation, I would have to actually train it with more data that sounds like this. All right. We've gone through a lot of stuff. We've talked about speech recognition and why it doesn't work, collecting data, how to do it, be friends with podcasters, essentially. We talked about training models using Create ML. We've talked about metrics for analyzing our models, the accuracy, the little bit of the precision, the recall. We've talked about augmenting our data to improve our models. So when you don't have enough data, you can augment your own data that you have to help get a little bit further. We've talked about active learning, which is a very promising way to get improvements to your model without having a lot of data. Just train on the hard examples. And there are lots of bad jokes. So what's left to do? Get more data, I guess. This is where a lot of the data and the code is going to be. This repo right here is on DAG's Hub. It's going to be, I can't put up Joe and Charles's audio there, but I can put up the audio from the people speech up there. I'm going to put a lot of the example codes and my counter, which was the live demo, which I wish would have worked, but didn't. So if you want to check that out, you can check out that repo there. I'll put it up there hopefully by the end of the week, but it might be a little bit later than that. I've been working with DAG's Hub for a couple of months to try out their features, and it's basically the GitHub for data scientists. So instead of just versioning code, it can also version data, which is important for being able to reproduce your models and your experiments. Thank you. Oh, sorry, there's one more thing. In the code that I wrote for that counter, which will be on that repo eventually, I created a microphone manager singleton class to handle all of the input audio from the microphone. The best thing about having a singleton called a microphone manager, when you instantiate it, you can call it a micromanager. All right. And that's my last joke is Bill Lumberg. All right. Thank you. Can I put my sound bites on Kaggle? I will have them on that DAG sub repo, so you can be able to download from there. It uses an open source, behind the hood, it uses an open source program called DVC, which is kind of like the Git for data. So it allows you to version data and stuff like that, and you can just pull it down fairly easily. It's much easier to use than Git LFS or something like that. So I'll have that there, yeah? So you're asking why not train a natural language processing model? So you're talking about like an off-the-shelf model that already exists. Why not train it on your voice with 3 sentences or something like that, and it'll learn how to say ums and stuff like that? That's a good question. That's one of the reasons why I talked about this is not the right tool for the job. And this is also why it's called how not to create an detector. But let me get back to this. So that would work for you then, right? If you wanted to create a tool that you could market to, say, other people, like my product market fit, you would need to be able to work on a lot of different people, a lot of different voices, a lot of different pitches and stuff like that. Yeah. Let me get him first, and then, yeah, go ahead. Okay, so the question was, I went through and I split up files that were already naturally, where Joe and Charles were naturally saying uhs and ums in between their recordings, and I split them up and then listened for which ones are uhs and ums and sorted them that way. You're asking, would it be the same if I just went to Joe and say, can you say 10 times for me, and go to Charles, can you say 10 times for me? My gut feeling is when you say in a natural way, in a natural environment, you pronounce it a little bit differently than when you say like when you're trying to. My live demo again, which I swear works, it would detect when I would stutter and say but it would not detect when I would say how to create an detector, because I think part of the thing that the machine learning models can do is they see patterns in the data that you and I might not see. So for instance, it might be the little stutter of a pause between before you say and after you say before you start speaking again, that it just says, okay, so an is actually this word but also it's got like a little bit of a pause before it that's between this length and this length. I don't know, I'm just guessing right now. So it would be hard to recreate that naturally just by say 10 times. That's my gut feeling, but it'd be something that we can test out. This is all about science and experimenting, so that's something that would be worthwhile testing, I think. All right, thank you.